Okay, so what we have now is the idea, like what is actually the physical processes that will give the leading contribution in every order. And all this is based on the idea that we're looking at high densities. So this idea then allows us to address also the higher orders perturbation theory. So just generalizing of what we have found from our second order analysis, this argument on the phase space volume in nth order perturbation theory should just be, or is just identical. So in every order interaction, we want to have the maximal number of independent electron hole excitations, meaning in an nth order process, we want to have n independent electron hole excitations, because they give the largest phase space volume, so are the most probable to occur in the high density. So the above picture, so above discussed before, readily generalizes to interaction processes of higher order. That means in the high density limit, the dominant or the leading contributions to the free energy should contain, so generalizing what you found in second order, just one free momentum summation over the Fermi surface, summation over the Fermi surface per interaction process. That means in second order we want to have two independent summations in Fermi surface, and in an interaction process we want to have n independent p summations. Okay, one free p summation over the Fermi surface per interaction process. So one free Fermi summation means, like physical, we said, well, the most probable contributions are those where we have then the maximum number of independent electron hole excitations. So in an nth order process, we want to have n electron hole excitations involved. So in an nth order process, like in the fourth order, we want to have 4 different electron hole pairs, okay? And so on in an nth order, like in the second order, we have those, and 3 we want to have 3 independent electron hole pairs, and so on, okay? So we want to have in an nth order process, we want to have n independent electron hole pairs, and then we can, okay, now I draw this really bad. But then we can arrange, like in the nth order, we can arrange these electron hole pairs just in a way that allows to perform. So now at the nth order process we should have n interaction lines. So this would be a fifth order process where we have 5 interaction lines, okay? Fifth order process, and we want to have 5 electron hole bubbles or these polarization bubbles, okay? And this generalized. This means then that in every order we will always find these ring structure diagrams which meet this criterion. Okay, so only the diagrams of ring structure, like here for the fifth order, but this already generalizes, meet this condition. Okay, so this one can really see. And also an nth order process should involve n independent electron hole exchanges, so n bubbles, and then you have to connect these n bubbles, make out of this a connected diagram with n interaction lines, and the only way is to connect every two lines and then make one connected ring. Okay, so this then tells us, however, that we can actually write down the nth contribution in this approximation. So in the large density limit, we can write down the nth order contribution to the free energy. And let me just write it down in an approximation where we only keep the ring structure diagrams, so only those with n independent electron hole exchange. This is called the nth order contribution to the free energy in this approximation, which is called RPA, random phase approximation. Okay, so this is how it's called in the literature. We first write down the result and then explain, motivate the prefactors, and make some comments. So in the nth process, we should have n interaction potentials, and we should have n particle hole bubbles appearing. So this is just here one particle hole bubble. Okay, this GP, P plus Q with a summation of T is just one of these particle hole bubbles. And now this to the power of n corresponds to having n bubbles and n interaction lines. So this would be like this order. And then okay, let's make some comments on the prefactors that are appearing here. So first, some general comments for keeping only ring diagrams is called RPA, coming from random phase approximation. And this is for historic reasons. And actually one has to be careful, for historic reasons, one should be careful because there is more than one approximation that is called RPA. So caution. More than one approximation that's called RPA. Okay, so this is very common. So let's comment here on the prefactor. So the structure, I think, is clear now. So this is again the bubble and the interaction line in nth power. So we should comment on the prefactors. So we said that, well, what we start out from would be actually T over 2L cubed to the power of n with a prefactor 1 over n faculty. This would be what we get from expansion of the partition function in nth order. Okay, so now we have the 1 over n faculty became a 1 over n. So let's first see so let's explain the prefactors. So the 1 over n actually can be understood as the 1 over n faculty from nth order of the partition function in the interaction. Okay, so expansion of the exponential in nth order. And then we have like different ways how to rearrange or how to arrange these kind of ring structures. Okay, so actually we can like just permute the order of the rings, but keeping in mind that if we would just switch like diagrams, rotate all of them in the same direction, it doesn't make any change. So if we go then and look at the combinatorics, we get a factor of n minus 1 faculty combinatorial factor of rearranging the diagrams without like rotating the thing. Okay? This is like factor n minus 1 combinatorial factor of arrange like combinatorial factors arrange n with interaction vertices. Okay, I read this now. Vertices in ring structure. Okay? Taking into account that, well, if you rotate all these, this doesn't change it. So this gives you n minus 1 factor, combinatorial factor, and faculty gives 1 over n. Okay? So this is one thing, and then we have to see where this 2 to the power n comes from. So again, from normal perturbation t, we would have a t over L cubed over 2, so 1 over 2. And so we have to understand the factor. This comes with a 2 to the n minus 1, so we multiply all this with a factor. Okay. Yeah, so it's. One thing, so the prefactor that I meant, we had in the beginning a 2 to the L cubed to the power of n. But now what we have is factors of 2. Every of these diagrams comes with a free spin summation. So this gives a factor of 2 for each ring, okay? So we have factor 2 to the n spin summation. And then we have another factor which is like what we do here is we have two kind of diagrams, like this part here and this part here, that we connected in some way. Okay? But what we can do is we can, in this diagram, we could exchange, like flip them in this way. Now, if we flipped all of them, then again we would arrive at the same diagram. So we have n minus 1 times the possibility to flip this line. So this gives a factor 2 to the n minus 1 from, how do I write this, flipping, like you can connect this way, this way, or you can just, so you know what I mean, you can just flip it, okay? Yeah? So this 2 to the n compensates this one here. This 2 to the n minus 1, I can write a 2 there and have a 1 over 2 here. Okay, so this explains the prefactors. And let's see. What else? So this is like technical comment, and just make one more general comment that I already said before. Like conceptual thing. So this is actually levar a N ainda por causa disso. Certo. Certo. So what we have, so this is like technical remarks, but conceptually we have managed now to identify in every order perturbation theory a certain class of diagrams that are the most relevant to the high density limit. Now this means that actually, as you can see, we can now sum like all the contributions from every order. So this is, I'll give the results. So what we can really do now is sum all orders perturbation theory. So we can arrive at an approximated form of the free energy where we took into account all orders interactions. However, in every process interaction, we only took into account a certain class of diagrams justified like by the high density that we're interested in. So there's some physical parameter control approximation. Now this then actually is a nice thing because, I mean, so I already said this before, no? So in the beginning we made this distinction. We said that perturbation theory always is kind of dangerous because what we're normally doing is we're doing perturbation theory around some reference point which doesn't allow any form of scalar expansion. So typically all perturbation theories are, or many perturbation theories are just asymptotic expansions where we shouldn't even try to sum infinite orders because it means an asymptotic expansion after a certain order just makes the approximation worse. Now, the reason for getting worse and worse results if you go to too higher orders was exactly the fact that in high order perturbation theory, the prefactor like of the interaction strength in some high order is small, but then the number of the combinatorial factor, like the number of diagrams you can generate in hence order, just exponentially grows and will at some point overweight like the smallness of the interaction strings. Now, we overcame this problem here by just looking at a subclass of diagrams. So restricting ourselves, identifying in every order perturbation theory subclass of diagrams which are the most relevant, allows us then to do an infinite summation, overcoming this problem of asymptotic series because we counteract this proliferation of exponential number of diagrams by just keeping a certain subclass. Okay? So this is conceptually important that we have managed, or we will see that one can manage to sum them all diagrams. So first we have managed to identify particularly relevant subclass of diagrams. And there is a physical parameter controlling the dominance of this subclass of diagrams. So we know if you go to the infinite density limit, then provide stronger than like the nth order contribution corresponds or is identical to the RPA contribution as this parameter that controls our density goes to 0. So this is like in the very high density limit. And the high density limit that we are interested in where interactions are also weak. This approximation becomes better and better. Okay? so that's conception is an important part. Now in RPA approximation, you can then just sum we can sum the contributions from every order. Okay, now as Eric pointed out, there's a factor -1 to the power of n from each group of the diagrams. But then actually I made two mistakes because there's also a factor of -1 to the n from the expansion of the e to the minus. Okay? So the overall factor is just the minus. Okay? So there's two factors which cancel. And if you then do some this contribution, well, you get 1 over n times x to the n, and sum from n equals 1 to infinity. This just gives a log, no? So what you find in the RPA approximation, you can find the free energy as being t per half. Sum that remains, the n with the power n becomes log, and here the p of q is introduced here as a short form to denote the polarization bubble. It comes to the 2 pi over L cube, and then the product of two means function of two propagators at shifted momentum, and this is called the polarization operator. Operator, and diagrammatically corresponds to this polarization bubble that appear in these strings. So all momenta here are the 4 momenta containing 3D momenta and mass particles. Okay, so this is the final result of a calculation where we managed to find a controlled parameter which allows us to make an infinite summation of perturbation theory. So it's infinite perturbation theory, and actually what was of great help for this was, well, first of all, set its diagrams in an efficient way to represent the interaction process, but we also saw that, I mean, like this kind of phase-space argument is harder to see like in the analytical expressions than in the diagrams. So this is, we could see really that you have the 3 summations. And we could also just see the physical process by seeing, well, there's 2 different types of diagrams. One have 2 disconnected propagator lines, and one just have 1 connected diagram. And this just corresponds to different physics. And in this case comes with different probabilities. Describing different physical probabilities come with different physical process comes with different probabilities to have. So this is a first example of an infinite order expansion. Okay, so then let me just write down what I said already. Like, well, in the beginning we had the statement, in the beginning of perturbation theory, we had the statement on asymptotic expense. So how does this connect to comment on asymptotic expansions? Well, So I said we managed to identify a subclass of relevant diagrams, so keeping only the subclass of most relevant diagrams in each order perturbation theory, of most relevant in each order perturbation theories. We beat the exponential proliferation of number of diagrams and therefore manage to arrive at the final result. Okay, so this is again conceptually important that we managed to do this, and let's see. Okay, questions or?
Esses diagramas que são desconsiderados, de fato, houve uma análise para mostrar que eles, nesses limites, não vão. Porque, nossa, eu fico.
Certo, não, com certeza, certo, isso deveria olhar qual seria a literatura, sim, mas você vai ver que vai aparecer o parâmetro RS, que vai controlar que é a velocidade. Pode ser que é no Mayhem também, eu teria que olhar. Tá? Mais perguntas? Ok. Vou só mais escrever alguns resultados. Certo.
Esse lembra de um momento que você está meio que trocando os graus de liberdade da sua teoria?
Pois isso a gente vai ver. Ok, o que a gente vai fazer ainda? Tem ainda, bom, uns resultados que eu vou ainda mencionar. O que a gente deveria verificar ainda é que a gente viu que teve um problema físico quando a gente olhou a second order perturbation theory. Isso foi relacionado que a gente não está tomando em conta o screening. Tem uma maneira agora de ver que pegando essa infinita ordem, vai resolver esse problema. E fisicamente, esses bubbles que estão aparecendo, os polarization bubbles, bom, eles exatamente descrevem isso, que quando você você faz um hole no Fermi seed, aí você vai rearranjar, assim, de certa forma, você vai polarizar o meio na volta para blindar a carga aqui. E exatamente são esses polarization bubbles que estão aparecendo. Então a gente ainda tem que verificar que essa RPA approximation vai fazer um screen detection potential que vai cuidar desse problema da identity of states que a gente encontrou. Então isso é uma coisa que a gente ainda vai discutir. E depois, exatamente, o próximo passo vai ser, de novo, conceptualmente, que a gente está vendo aqui que o grau de liberdade, na verdade, não precisamos mais pensar, de certa forma, sobre os fermions, mas os fermions só aparecem em esses loops que estão escrevendo, de certa forma, um potencial efetivo. Isso a gente vai ver que a gente, para esse problema, pode, começando de novo com os eletrões, através de um método conhecido como Harvest Autonomous Transformation, derivar uma teoria efetiva, que não é mais baseada nos eletrões.
Então, baseado na parte intrometerida os campos efetivos. Né?
Exatamente. Isso vai ser depois de resolver essas coisas, que talvez seja mais uma aula. A gente vai introduzir, em termos gerais, como introduzir teorias efetivas. O primeiro exemplo vai ser exatamente esse aqui. E depois vai ter outras ideias. Então, a ideia depois, vamos ver quantas aulas a gente ainda tem, mas a gente vai exatamente para introduzir um método geral, como gerar teorias efetivas. O primeiro exemplo vai ser esse. Depois, a ideia seria estudar outros exemplos, que sempre é baseado. Vamos estudar um outro problema, não weakling tech em eletrônicos, mas vamos, sei lá, uma atração positiva entre os elétrons mediados pelos fótons. Primeiro se faz a análise em termos de diagramas, você vai ver que um certo tipo de classe de diagramas é a mais relevante, controlado por um parâmetro. E uma vez identificado esse tipo de diagrama, você vai ver qual vai ser o grau de liberdade efetivo em que você deveria formular a teoria efetiva. Aqui a gente já vai ver como conectar esses bubbles aparecendo aqui com um grau de liberdade, que vai ser a densidade nesse caso. Então vai ser sempre assim baseado. Você faz primeiro a análise em Feynman, você está realizando que tem, nos exemplos que a gente vai ver, certos subclasses de diagramas que são dominantes, e esses consistem tipicamente de 2 eletrões, né? Como esse aqui. São 2 eletrões. 2 eletrões formam um bóson. Então deveria ter uma forma mais efetiva de, em vez de falar dos eletrões, já falar nos bósons. Esses são os teoria efetiva. Tá? Mas isso, eu acho que na próxima quarta a gente vai fazer isso, vai começar com isso. Mas primeiro tem que ainda terminar isso aqui. Tá? Bom, então deixa eu só rapidinho terminar isso aqui. Que é, bom, so the polarization bubble, which depends on the form momentum, again can be calculated like for the 3D case that we are considering, and what one finds is the following result. Maybe we make an exercise out of it, or I have to look up, I think it's again, I have to look up the book where you can read it if you don't make an exercise from it. Or you can just try to do it yourself, I don't know. How hard it is actually, might be not so easy. But what you find is that this polarization operator in the 3D case can be expressed in the following form. So it's a function of the external, like the mathematical frequency momentum that enters it. You have the log, you have this prefactor, and this mu 0 is the density of states. Density of states of electrons at the Fermi surface. So at momenta, so the density of states at energies at energies corresponding to Fermi energy, and density of states, I should be here more careful, so it's of the non-interacting electrons. And it's the density of states per volume. So there's a factor, you can count 1/L cubed. Okay? So actually, in our case, this would be m Fermi T squared. So that's probably left as an exercise. So that's one comment, and of course all physics now is in this polarization operator, so one has to understand this, what this does, and see how this describes some screening. So this we are doing just next lecture to see how this leads to the screen detection potential, and which then cures the problem with the density of states that we found in second order. But then let me just make some statements which we don't calculate, but if you insert this here into expression for the free energy. And then you still have to perform a final sum over the Q and the bosonic omega n. Which is far from trivial of doing. So again, who's interested can find details in the book by name, but it's like not an easy task. Then one can arrive at the following. So one finds that the free energy is given by the zeroth order contribution that we discussed, and that we said scales as number of particles divided by r squared. Then we have the first order contribution, which we also discussed from perturbation theory, and we found is proportional to Rs. And then there's a contribution for n being larger or equals to 2. Some people call this the RPA contribution. Some include also the first order, so that's again some, depending on the taste. So this would be the contributions now starting from second order and summing all the ring diagrams. And if you do this, what one can show, again not easy, that this measured in energies of the Rydberg energy and divided by the number of particles is what? Minus the number for 2 plus then 0, 0, 6, 2, 2, and the log of Rs, okay? Plus orders in Rs which vanish as Rs goes to 0, so vanish in the high density limit. Okay. So you manage to derive now the remaining terms in the free energy, where, as we already found from lower order perturbation theory, everything indeed is controlled by this dimensions parameter Rs, and you manage to sum all the other diagrams into a contribution of order Rs, zeroth order into log. And actually this is the result first derived by Geldman and Brückner. Who's interested in the book? See more details. Okay, so this is like the result that we are looking for. We identified at the beginning the parameter which tells us when interactions are weak, so which is the high densities, which then turns out is also the parameter that controls in every order perturbation theory, like what are the relevant diagrams, which we can then sum through the right. So what remains to do, as said, is just to confirm that keeping now this infinite series will cure the problem in the density of states. So this is one thing. So see how like a screen interaction potential arises. So probably this is one lecture, and then we start with the effective series. Oh, it's a okay. And whoever